capacitance due to introduce of a metal slab. It is not a dielectric. I have introduced a metal slab of thickness T. Okay. So how we have to calculate it? Let's see. It is a capacitor. I have introduced a metal slab of thickness T. We know the thickness for a capacitor, it is D. So T portion is occupied by the metal slab, and here the positive charges will come just earlier. Here it is the negative charges, and this is the electric field E naught is acting downward from positive to negative. Now here is an important question. What we have seen for the dielectric? In dielectric, we have seen one concept that is called polarization. Polarization. Polarization means the positive and negative charges are just arranged in opposite side. So in positive, the negative charges will arrange, and in negative direction, the positive charges will arrange. That is occurred for case of dielectric. But here, it is a metal slab. And we know, I have written here, we know in metals, there are excessive number of free electrons. In dielectrics, whenever we have read it, I have already told you that in dielectrics it is an insulator. So there is no free electrons. So no electrons can move here and there. But for the case of the metal, is enormous number of free electrons are there. So it is not possible for a metal slab to be polarized. It is not possible for a metal slab to be polarized because their whole charges will moving here and there. Charges mean the free electrons will moving here and there. So that's why inside the metal slab, electric field is 0. Here the electric field is 0. Why? The reason is that here huge number of free electrons are there. That's why polarization, what we have seen for the dielectrics, it will not happen here. Okay, so apart from this portion T, the rest of the portion is D minus T, and in D minus T portion, the electric field is E naught, right? So potential V equals to E naught into D minus T plus E into T, where E equals to 0. So E naught into D minus T, and this portion goes to 0 as E equals to 0 for the case of metal. So this is the potential. So E naught into D minus T, E naught means sigma by epsilon naught into D minus T. And here capacitance C equals to Q by V. So Q equals to, again it is sigma A by sigma by epsilon into D minus T. Sigma will be cancelled out. That is epsilon naught A by D minus T. Here also you see one very interesting thing is there. For parallel plate capacitor, it is C naught equals to epsilon naught A by D, and it is D minus T. That means definitely in this case also the capacitance is increased as the denominator is decreased here. You see, this is the denominator. Denominator is less than D. D minus T means less than D. So the capacitance will be increased. So we have to use metal slab inside the parallel plate capacitor to increase the capacitance? No. Why? if we can able to do this by metal slab, then there is no need of introducing dielectric. Why? We cannot able to use the metal slab. Though using metal slab we have seen the capacitance is increased. The problem is that due to the presence of positive charges here, as it is a metal, so due to the induction here negative charges will automatically come. Okay, and here positive charges, but they will flow. So from here the positive charges will come here, and after some time the negative charges will come here, and there will be a connection between them. We want not the two charges will pass from one to another. So if it is gone, then the charge storing capacity will be less. But here, as we have introduced a metal plate, this metal plate will just try to acting like a communication, like to make communication between the two plates, so that the charge, initially you see the capacitance may be more, but for a certain time period if you keep it like this way, then it will just start losing charges, and after some time you will see there is no charge. If you connect it together, there shouldn't be no charge. So that's why we don't use metal slab physically. Okay, we use dielectric, because dielectric is an insulator, it cannot carry charge, but metal slab can do this. Okay, so this is capacitors with dielectrics. Now I'll just tell you some interesting smaller thing which is mainly used for competitive exam. So it's very important. So I'm just telling you some extra things in capacitor. Extra thing in capacitor. We know for parallel plate capacitor it is epsilon naught A by D. But if the parallel plate capacitor is arranged like this way, so assume it is X, it is X dash, it is X double dash, it is X triple dash. So all these are parallel to each other. So here it is positive, definitely. This is negative, it is positive, it is negative, it is positive, it is negative, it is positive, and it is negative. So here we have taken a series of parallel plate capacitor. Okay, so in this case what will be the capacitance? For a single parallel plate capacitor, so we know it is epsilon naught A by D. For this type of series, that will be, you have to remember it, capacitance C will be n minus 1 epsilon naught A by D, where we have taken this gap should remain D always. This gap should remain D. So then the capacitance will be n minus 1 epsilon naught A by D. What is n? N is number of plates. So how many number of plates are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 plates are there. So for that case, here it will be 8 minus 1 epsilon naught A by D. Okay, so it is 7 epsilon naught A by D. So this is a very interesting thing, and you might be thinking, sir, from where this n minus 1 has come? You have to show it. If I have done the calculation, that is very long thing, and to tell the truth, there is no calculation is given in the book also. We have to remember this thing for short answer type of questions. Okay, next Instead of this, if it is kept like this way, it is only one type that I have just going to show you now. That is number 2. That assume so it is x, it is y, it is connected with negative, it is positive, so it is positive, it is negative, it is negative, it is positive. So if this type of arrangement has done, you see how many plates are there? 4. Here the calculation C will be n minus 2 epsilon naught A by T, and for this case it is 4, so it is 4 minus 2 epsilon naught A by T. This 2 epsilon naught A by T. Many times this type of question has come in NET, GE, this competitive level paper. It's a very common questions, as we have done capacitance and it is very important chapter. That's why I have just introduced this type of smaller thing you have to remember. If you know that, then it is the easiest question, but if you have not known that, it seems to be the hardest. Okay, whatever you have done. Next we'll go for a very smaller thing, that is charge distribution. Charge distribution, though it is, if I'm telling that whether it is very important, no, it is not a very important thing, but then also we have to see charge distribution. What is charge distribution? Assume you are having two spherical conductors. If you connect it parallel to each other with a potential V, okay, then assume their capacitance are different. It is C1, it is C2. If you arrange it like this way, so the potential should be same, because as it is connected with parallel, the potential difference will be same, but the charge capacity, that is different. Assume it is Q1, it is Q2. Okay, Q1 and Q2. So from here we can write that we know Q equals to CV. That means V equals to Q by C. So from here V equals to Q1 by C1 and V equals to Q2 by C2. You see, Q1 by C1, Q2 by C2, potential is same. These two equations are same. So we can write Q1 by Q2 is equals to C1 by C2. From this equation we can write, because we can say another step, and apart then we can go here, then it will be easier for you. Q1 by C1 equals to Q2 by C2, and then Q1 by Q2 equals to C1 by C2. What do we want to say from here? We want to say that the charge is being distributed by a ratio with the ratio of their capacitance. So what will be the ratio of the capacitance? That will be the ratio of the charges also. Again we know that for spherical conductor, C equals to 4 pi epsilon naught R, we have done earlier. Here also, instead of C1, assume this radius, it is given R1, this radius is given R2. So if you write here Q1 by Q2 is equals to 4 pi epsilon naught R1 by 4 pi epsilon naught R2. So it is R1 by R2. Here also one another thing, that charge is distributed by a ratio with the ratio of the radius of the sphere. Okay, that is also one interesting thing. Again, one more interesting thing is there. If we want to find charge density, that is sigma 1, that is equals to q1 by 4 pi r1 square. Sigma 2, that is q2 by 4 pi r2 square. If I am taking a ratio sigma 1 by sigma 2, it will come in q1 by q2 into 4 pi r2 square into 4 pi r1 square. So 4 pi will be cancel out. Q1 by Q2 equals to R1 by R2. We have done earlier. It's R1 by R2 into R2 square by R1 square. R2 R1. So it is R2 by R1. So we can write sigma 1 by sigma 2. It is R2 by R1. Now you might be thinking, sir, why we have done this in capacitor? So our target is to know how the charge is distributed among a spherical conductor. That we just want to show you here. Nothing else. I just want to show how the charge is distributed. We can see the charge is distributed as per the ratio of the capacitance, as per the ratio of their radius, and the charge density as per the reciprocal of the ratio of the radiuses. There might be some small questions can come, so that if you know this equation, you can easily do that small questions very easily. If I'm talking about board, is it coming in a board paper? No. If you are not one interested in competitive exam, then you can skip that portion. It is not important for you. But it is important if you want to give any another exam. Then this type of questions are coming. So as I have done, I want to make that capacitor should be clear so very much that any type of question from anywhere can you able to do. That's why I have just done this extra thing. That's why I have made a heading extra thing. If you are not interested, then forget. You can skip from extra thing. Before extra thing, the important part is told. It is not important for you. Next, one thing is told, that is loss of energy due to charge distribution. Loss of energy due to charge distribution. What is loss of energy due to charge distribution? Let's see. Okay. Loss of energy means, assume initially I have connected one capacitor with a potential difference V1. Assume the capacitance is C1 and the charge induced here, that is Q1. Okay. If you do it here, so from here you can write Q1 equals to C1 into V1. Okay, and here if you want to find the energy, so energy U equals to half C1 V1 square. If you connect another capacitor of capacitance C2 with a potential difference V2 and the charge storing capacity is Q2, then we can write Q2 is equals to C2 V2 and energy U2, it is U1, equals to half C2 V2 square. Okay, separately connected. Now what we have done? Now we have taken these two capacitors parallelly each other. Okay, and then we connect it with a potential V, so that the charge will be same Q1 and Q2 and the capacitance is C1 and C2. So from here we can write that V equals to C1 into, Q1 equals to C1 into V. If we connect these two parallelly, it is Q1 equals to C1 into V and Q2 equals to C2 into V. Because as it is parallel, the potential difference should be constant. Now from the previous portion, if I want to do total charge, that is equals to Q, that is equals to Q1 plus Q2, and here it is C1 V1 plus C2 V2. And here if I find total charge Q equals to Q1 plus Q2, and it is C2 into V plus C1 into V. Okay. If I am telling total energy, that is U1 plus U2, that is half C1 V1 square plus half C2 V2 square. If it is told here total energy, so here total energy U equals to half of C1 plus C2 into V square. Why C1 plus C2 I have done? Simple thing that here it is connected in parallel, so resultant capacitance will be C1 plus C2 into V square. Now, if it is talking about the total charge, you see, the steps you want to understand, you have to fill it. What will be the total charge here? If I am talking about total charge, that is Q equals to Q1 plus Q2. So, this total charge will be same. Total charge will be same, that is C1 V1 plus C2 V2 is equals to C1 V plus C2 V. Total charge will remain constant, and from here we can write V equals to C1 V1 plus C2 V2 by C1 plus C2. Okay. Now you might be thinking, sir, what is the need of doing? So by that we can understand what is the V we have given here. Now, as you have connected parallelly, initially you have connected separately, there you have got energy. Whenever you have to connect parallelly, then there will be a loss of energy. Okay, so what will be that loss? That we want to find here. How we have to find that energy we have got earlier, that is we have written here, it is UI, and whatever the energy we have got after connection, we have to make a minus, and by that minus we will understand that what will be the loss of energy. So I am erasing this thing. If you want to copy, pause it and then see it. Okay, so here I am writing loss of energy delta U is equals to UI minus UF. Now you might be thinking, sir, till now we have learned whenever we have to find the difference, we have to do final minus initial. But why we are doing initial minus final? See, later you will come to know that initial energy is larger than final energy. That's why the energy is lost. And so that the loss of energy will come in positive, we have done initial minus final. So if you do it, half C1 V1 square plus half C2 V2 square minus half of C1 plus C2 into V square. Now you see we have finding a value of V. Put the value here. If we take a common half, it is C1 V1 square plus C2 V2 square minus C1 plus C2 into, instead of V square I have to write this one, that is C1 V1 plus C2 V2 by C1 plus C2 whole square. Okay, so here, so complete the third bracket. Now we have to calculate it. Calculation is little bit of longer. So half of C1 V1 square plus C2 V2 square minus C1 plus C2, and here C1 plus C2 square. One, it will be cancelled out. So it is C1 plus C1 V1 plus C2 V2 whole square into C1 plus C2. Okay. So C1 plus C2 will be multiplied here. So I am writing directly. you might be boring of that calculation. See, it is also, I'm telling, it is not such important thing. If you are not interested, you can stop the video here. It is not like that you have to remember this. If you have not done also, I'm telling you, no problem. So if I multiply, that is C1 square V1 square plus C1 C2 into V2 square plus C2 C1 into V1 square plus C2 square V2 square. We have multiplied it, C1 plus C2 into here, minus C1 V1 square minus C2 V2 square minus 2C1 C2 V1 V2 by C1 plus C2. So we can take C1 plus C2 out. Okay, so it is 1 by 2 C1 plus C2. We are taking outside. Here you see C1 V1 square, C1 V1 square, C2 V2 square, C2 V2 square. It is gone. Now one thing should be common again. So we will write it together. Half of C1 into C2 by C1 plus C2. So from here you see C1 C2, C1 C2, C1 C2. I can take common. It is coming V1 square plus V2 square minus 2V1 V2. So A square minus B square, A square plus B square minus 2AB. So A minus B whole square. That equation will come. So it is half C1 C2 by C1 plus C2 into V1 minus V2 whole square. Okay. So this is the loss of energy here. And you see one thing, C1, C2, C1 plus C2, all these things are capacitance, and capacitance are always positive. And V1 minus V2 whole square, that is also positive. So here we will get a positive value. What does it mean? It means that if you connect capacitors in a combination, then some energy will be lost. And where this energy is gone, the lost energy is increasing the heat energy of the circuit. So this energy is basically increasing the heat energy, means it is used as a, it is means not used form, it is just giving the heat energy only, no other use of this energy. Okay, so this is the extra thing we have done. If you give me one single time, I will give one more interesting thing. So you might be thinking, sir, what is this going on? Continuously you have given some extra thing. See, in capacitor many more things are there. I am just trying to cover everything so that it will be helpful for you little bit. Okay, so now we'll go for the another thing, that is spherical capacitor. The last thing I'm telling you, after that I will not increase it anymore. Spherical capacitor. What is it? I'm doing very fast. So assume two spherical shell. One, it is Q, another it is minus Q. One radius is R1 and another radius is R2. It is kept like this way. We have to find the capacitance of this capacitor. How we have to do this? Let's see. So to do it, what we have done, we have to find the electric field. So to find the electric field, first we have to assume a Gaussian surface of radius smaller. So a Gaussian surface of radius r is taken. Okay, so a Gaussian surface we have to find out. So it is the easy way to finding the electric field. We know phi equals to integration of E dot ds. Okay, and here you see the electric field is acting outward. The area is also acting outward, so we can write it is E ds cos 0 degree. So it is integration of E into ds. Okay, integration of E into ds. So that should be total charge Q enclosed by epsilon naught. How much charge is introduced here? That is small q. So it is Q by epsilon naught. E into ds means what is the area of the sphere? That is 4 pi r square into Q by epsilon naught. So it is E equals to Q by 4 pi epsilon naught r square. That is the electric field. Now we have to find V. V equals to minus of E dot dr, its integration. So it is minus of Q by 4 pi epsilon naught r square into dr. Now here one thing we have to see, that is what should be the limit. You see, the limit is from outside it is minus q and inside it is capital charge q, that is plus q. So always we know the charge is coming from negative to positive. Okay, that's why the charge is increased in capacitor. So it should be R2 to R1. Okay, I'm doing it little faster. Basic principle is same. We have to find V and we know C equals to Q by V. So we'll put it here and we'll get the answer. So if I find V here, so V equals to integration minus Q by 4 pi epsilon naught integration 1 by r square dr R2 to R1. If I integration 1 by r square equals to minus 1 by r, so minus Q by 4 pi epsilon naught minus 1 by r, R2 to R1. So you see, minus minus will be cancel out. Minus minus will be cancel out and it is coming Q by 4 pi epsilon naught 1 by R1 minus 1 by R2. 1 by R1 minus 1 by R2, that is your V. Then C equals to total charge, that is small q by V. So small q by Q by 4 pi epsilon into 1 by R1 minus 1 by R2. Okay, so it is little bigger. Q will be cancelled out, 4 pi epsilon will come up, 4 pi epsilon 1 by R1 minus 1 by R2, so that means R1 into R2 by R2 minus R1. This is your capacitance in spherical capacitor. This is, that is C equals to 4 pi epsilon naught R2 into R1 by R2 minus R1. That is the capacitance for spherical capacitor. Now from here you have to see one basic special case. Now you might be thinking, sir, now it is going beyond our head. No, I'm not giving any difficult thing. So see, we have seen it is 4 pi epsilon naught R2 into R1 by R2 minus R1. So here, if R2 is very greater than R1, R2 is very greater, that is almost infinity. Infinity means only one sphere is there, another sphere, okay, it is at very long distance. What it will be? So R2 minus R1, that is nearly equals to R2. So if I put the value here, C equals to 4 pi epsilon naught R2 into R1 by R2, 4 pi epsilon naught R1, that is capacitance of spherical conductor, that we have done earlier, that if the radius is R1, it will be 4 pi epsilon naught R1. Okay, so just like that we can do the capacitance for a cylindrical capacitor also. We will not do it here, that will be your task. Let's try it. This is a cylinder, that is outer surface, it is the inner surface, the radius of the outer surface is R2, radius of the inner surface is R1 and the length is L. Find the capacitance. That is your task, that is your homework. You will do it, okay? And that is up to today's work. Thank you very much. Today we have done little large, okay, because many day we have not come, we have not coming for discussion. That's why we have done little more. Thank you.